Howdy, and welcome to a redo of lecture number 39. So my apologies for those of you that depend on the online lectures. The video equipment was working in the classroom, but obviously not the audio equipment. So I'll just go ahead and redo the lecture and cover everything that we discussed in class. So the first thing that we provided were a couple of announcements. One actually happened to be related to Lab 3, but that due date has now passed, so that's no longer a relevant announcement. But the second announcement is related to Lab number 4, and of course Lab number 4 will be due on Monday, May 9th, and of course that's due at the 11:59 p.m. Due date time, right at the very end of Monday, May 9th. And then the second announcement was related to exam number 2. So exam 2 will be released on Thursday, May 5th at noon, and will be due 24 hours later on Friday, May 6th, also at noon. And so both Lab 4 and Exam 2 are going to rely on what we cover in the chapter that we're about to start, which is Chapter 6, Spark Ignition Combustion. So it relies on material covered today, which is lecture 39, and then lecture 40, and lecture 41. Of course, ordinarily we would have 42 lectures during the semester, but with the freeze and the canceling of classes way back in February, we've been diminished to just 41 lectures, okay? Okay, so we correspondingly started our chapter on spark ignition combustion. And so this is chapter 6 material. And basically, one of the things that we highlighted was the fact that this, of course, is now peeling back the next layer of the onion, where if you think about the fact that we developed back in chapter 3 this heat engine analysis that, as we've already discussed, was inaccurate because we didn't include combustion, which is a reality of internal combustion engines. And so we then learned a lot about combustion and balancing stoichiometric reactions and calculating adiabatic flame temperatures, et cetera. And then we blended those two together, the combustion material with the heat engine material, and created what we called Chapter 5, the fuel-air cycle analysis. And of course, at this point, you all are experts at that, since that was part of your lab number 3. But there was still a deficiency in even that fuel-air cycle analysis, which I didn't really deeply delve into. But it was present nonetheless, and that's the fact that for our fuel-air cycle analysis, even though we were modeling combustion, we were still doing it in very simple thermodynamic terms, right? In other words, we would allow combustion to occur either as constant volume, constant pressure, or a combination of the two, what we, of course, call the limited pressure analysis. And none of these three are realities of what actually takes place in an engine. Even if we have the most reactive fuel and we introduce the fuel in such a way that it reaches a reaction temperature at the moment that we want it to burn, it's still going to require a finite amount of time to commence that ignition process and generate the radicals that are needed to lead to combustion and eventually do the what we call the high temperature heat release, or the exothermic reaction, where we oxidize carbon monoxide and we oxidize OH, the OH radical, and that's where we get our most substantial exothermic heat release, which is, of course, the raising of temperature and pressure within the cylinder and allows us to have a work transfer process during the expansion stroke. So all of those processes, that ignition, the development of radicals, and that high temperature exothermic heat release, that all takes a finite amount of time to execute. We can't just release the spark, for example, and then assume that there will be this instantaneous combustion process where it all happens and we go from, say, a fuel like methane, CH4, directly into CO2 and H2O, right? That's not really what happens. What happens is you have a species like CO4, and it decomposes into various radicals and intermediate species, and these radicals and intermediate species are essentially what ultimately lead to the final oxidation of carbon monoxide to CO2 and hydroxyl and hydrogen atoms to H2O, okay? But there's several steps as we go from this CH4, right, say our initial species, to our final species, which is CO2 and H2O. There's literally dozens of steps that occur in this process of oxidizing, say, even a simple hydrocarbon like methane, okay? And so we're actually not, unfortunately, going to be able to get into these details that we describe here in terms of that detailed combustion chemistry that takes place during fuel oxidation, but we can at least think about the finite nature of combustion, and we can try to model that in the context of things that we've already talked about this semester, as well as things that we know we can measure and know that we can relate to in terms of global operating parameters like spark timing and EGR level and fuel air equivalence ratio. And that's really what we're going to focus on in this chapter, is starting to dissect these various details of the combustion process, okay? And of course, as I've mentioned in class, this is the last layer of the onion that we'll be peeling back, with us only having 3 lectures left, this one and then the 2 next week. There's only so much material that we'll be able to cover in those 3 sections, and so we'll only be able to go so deep, right? But it's good to remember that there's still layers deeper, right? We've still not peeled back the deepest layer of the onion, which, by the way, we don't really know. This is a reason why IC engines are still a major area of research, and why I myself have built a career around researching internal combustion engines. The other item that I'd like to note is that this chapter will, of course, focus on spark ignition combustion. We do, in fact, have another chapter that I used to be able to cover in the class. I think I have added a lot of material in between since I first taught the class, and that is a chapter on compression ignition combustion. And so we certainly aren't going to have enough time to cover that before the end of the semester, but I will post a lecture for you that I had recorded previously about compression ignition combustion. I'll post that on Canvas so that you have an opportunity to watch that and view it at your interest, right? There won't be any assessments on it, so you're not required to watch it. It would just be an optional item to watch. Okay, so basically, what we for sure will be able to get through in terms of this semester, in terms of this next 3 lectures, are these first 3 bullet points, right? We'll for sure be identifying the primary processes of spark ignition combustion, how that translates into something which we call the mass fraction burn curve, which we'll be talking about in just a little bit. We'll also describe the factors that affect that burn curve for SI combustion. And of course, this is a major part of what you'll be doing for lab number 4, as well as exam number 2. And then we'll also, in fact, even today's lecture, discuss how ignition timing or spark timing results in what we call maximum brake torque. The one thing that we probably won't have time to get to is this last bullet point, which is to discuss combustion abnormalities such as fuel knock, right? And so if we're not able to get to that, I might move that to an optional video lecture where, again, I might be able to post this from a previous semester. I was able to get a little bit further when I last taught this class in 2020, since half the semester was moved to video lecture, and I'm usually able to go a little bit faster when recording video lectures as opposed to being in the classroom and being rigidly constrained to that 50 minutes. And so I do have an optional video lecture that I've created from the 2020 semester. And so if we're, and I'm pretty certain I'm not going to be able to get to it, but if in fact we're not able to get to it in the next 3 lecture periods, then I'll post this. And again, that would be an optional video for you to watch at your viewing pleasure. Okay, so let's go ahead and dive then into the details about spark ignition combustion. And of course, it's probably obvious, but just to state the obvious, what really distinguishes spark ignition combustion is the fact that we're using an external source of energy, explicitly a spark, to start and initiate the combustion process. Okay, and so you have literally a little spark plug that you can see in this first image here, this image A, and you can see it a little bit better here in image F, where you literally have a metal strap that extends into the cylinder, and there is a current that flows between the anode and the cathode of this spark plug, and it creates an ionized plasma that then leads to the ensuing combustion chemistry. Okay, and I'll talk a little bit more about that quote-unquote combustion chemistry here in just a little bit. But there's basically 4 major elements of spark ignition combustion, and they're largely captured in the 6 images that you see in the middle of the slide, and they're also captured in the cylinder pressure trace that you see at the bottom. This plot that you see down here, right? And so we'll talk about that as well in just a moment. But these 4 major elements of spark ignition combustion basically include, number 1, the spark release, right? So of course that spark release is this electric discharge by the spark plug. A high voltage current is flowed or is delivered to the anode of the spark plug, and there's an air gap between the anode and the cathode. And the voltage potential between those two is so high that eventually there's a spark discharge, or there's a voltage breakdown where a current is closed or completed between the anode and the cathode with that high voltage potential that exists between those two poles. And so when that voltage breakdown occurs, a current essentially establishes or forms between the two poles, the anode and the cathode. And so current begins to flow, and that's where you now have the visible plasma spark, or the visible spark arc, if you will, which basically just looks like, I'm sure you've seen sparks that you would see in videos and such, and basically that spark is the flow of a high voltage current between the two poles, and that then causes locally, very, very locally, within a few micrometers of that spark discharge, that creates a localized plasma, ionized plasma. That localized ionized plasma, if it's in the presence of a fuel-air mixture, causes the fuel and air to basically begin to react. Okay, but again, we have to be really careful by what we mean when we say react. It doesn't mean that we immediately go from, say, methane plus oxygen directly into CO2 and water. What in fact really happens is that ionized plasma begins to form what some people refer to as radicals, what other people like to refer to as intermediates. It all depends on how much of a chemist you are, I guess. But it basically forms species that are fragmentations of methane or some fragmented combination of either carbon and oxygen or hydrogen and oxygen. Okay, and so during the spark release period, it might form species like the methyl radical, for example, right, which would be CH3. It might form the hydroxyl radical, OH, right? It can form other what we would call intermediate species, right? And so, and it can be different combinations of different things. It just all depends on how the chemistry proceeds and what's involved in those various chemical reactions, okay? But that formation essentially occurs, of course, after the spark release, which is what we're capturing here in image or no, excuse me, image A is some period of time after that spark release. But the formation of these various radicals in intermediate species occurs during what is called the flame kernel development phase. Okay, and so the flame kernel development phase is what is being depicted in image A, B, and C down here in the middle of the slide. And that's basically where these various radicals in intermediate species get formed, is during this flame kernel development phase. Okay, and we'll oftentimes also refer to this flame kernel development phase. We'll also refer to this as the flame initiation period, and that's actually the language that I'll probably mostly be using as I go through this analysis of spark ignition combustion. Shortly after, or I should say, what ultimately brings the flame kernel development or the flame initiation period to a close is a transition into rapid burning, or what is more precisely referred to as turbulent entrainment and burnup. Okay, and this is what's depicted. And by the way, I'll go through these curves in more detail in just a moment. But that's what's depicted in images D and E that you have here in the middle of your slide. What happens during the flame entrainment period is essentially at the end of the flame kernel development period, this flame initiation period, you now have the small makings of a little flame. Okay, you now have something that, if you could look inside the cylinder and actually see the mixture and it undergoing these various chemical reactions in the beginning of this combustion process, toward the end of this flame kernel development phase is when you would perhaps start to see a little flame, okay, a little glow, if you will, of something actually happening, okay? Up to that point, it wouldn't look like anything's happening at all, right? And, if you could slow time down where microseconds began to look like seconds, you would literally go through, hundreds, if not, we'll say hundreds of those seconds, right, which would literally be hundreds of microseconds, before you would actually see anything happen, okay? But toward the end of that flame kernel development phase is when you would begin to see a flame develop near that spark plug area. And then almost immediately after the development of that flame, we then trigger into this turbulent entrainment and burnup period, okay? Now, the turbulent entrainment and burnup period is actually why we'll be able to have a combustion process that burns quickly enough that we can consume the entire mixture all within a single cycle, okay? And I'll talk more about that on in lecture number 40, where we talk about the time that's needed for a combustion process and the fact that turbulence is an absolutely essential feature of the operation of most internal combustion engines, okay? But that turbulent entrainment and burnup period ultimately results in the near complete consumption of the fuel-air mixture, meaning that's where we really engulf the mixture with flame, and we do the complete translation of reactants into full products of combustion like CO2 and H2O. And then the final stage, or the final element of SI combustion, is what we call flame termination. And this is just exactly what it is, right? Basically, at this point, the fuel-air mixture has been completely burned. There's no more fuel left to burn, and now the flame begins to quench through various mechanisms, right? Maybe it's starting to interact with the wall, which is substantially colder, and that can be a quenching mechanism. Maybe it's just literally running out of fuel, or maybe it's running out of oxygen, or what have you, right? There's something that's causing the combustion process to come to an end, and that leads us into this flame termination phase. Okay, so all of those elements that I just described are basically, in some form or another, depicted in these various images that you see in the middle of the slides, okay? And so image A, image B, and image C is essentially showing you Schlieren images, right? So it's showing you density differences of the flame kernel development phase. And so, and as you look at these 6 images in the middle of your slides, you're also going to want to train your eye on the pressure versus crank angle diagram that you have on the bottom of your slides, And you'll notice, of course, that top dead center is identified as 0 degrees, right? So if this is a 4-stroke engine, for example, it's going to go from minus 360, which would be the start of the intake process, all the way to plus 360, which would be the end of the exhaust process of the same cycle. And so top dead center after compression is at 0 degrees, right? That's basically the time period that we're most interested in, because combustion is going to have started some short period of time before top dead center, and combustion will complete in the major expansion work will take place, of course, after top dead center. And so this curve that you see here, right, this is your cylinder pressure versus crank angle curve. And there is a second curve on here, which is the mass fraction burn curve. And I'll go over the mass fraction burn curve here in just a moment after we finish discussing the various images. And so you'll note that on this cylinder pressure versus crank angle diagram, it's identified where the spark occurs, right? So the spark is released about 45 degrees before top dead center. And then you can notice that there's the alphabet letters that are shown on the diagram, A, B, C, D, E, and F. And those letters correspond to the various images that are shown in the middle of your slide, right? And so image A corresponds to this point on the pressure crank angle diagram, image B, image C, so on and so forth. So if you notice, image A, B, and C, these three images that are up here, these correspond to the flame development process, or this flame initiation period, right? Processes A through C. And again, remember that these images are Schlieren images, right? So they're showing you density differences. And the darker the image, the stronger the density gradient, right? And so you can, of course, see at image A, which is a period of time after the spark release, okay, that there's some, there's some visible gradation here in the upper right-hand corner, okay? And so what's important to note about that is, of course, that's at least about 8 degrees or so after the release of the spark, okay? And so even after 8 to 10 degrees after the release of the spark, you'll notice that there's only been a small disturbance, really, in the fuel-air mixture as a result of the release of that spark, okay? And then as we move to image B, the this area or this volume of this portion of the fuel-air mixture that has gradient differences, it grows larger in size and it gets a little darker. So by it getting a little darker, that's indicative of the fact that the density gradient is getting stronger, right? In other words, the density of this portion of the mixture is further departing itself from the density of the rest of the mixture, where, of course, we don't see any gradation in these other portions of the mixture at all. And then finally, we move to image C. And in image C, of course, the area where there's a gradient difference has grown larger and it's gotten much darker, okay? Well, that's basically at the point where you would begin to see a visible flame during the combustion process, right? And so as we go from image A to B to C, and in fact, even first having started with the spark, right? And so on our pressure diagram, this is our spark, and we go from point A to point B to point C, you'll notice that, in fact, it takes quite a long time for us to even observe anything, right? We can observe something on the Schlieren imaging because it's very sensitive to density differences, but you don't see any difference in the pressure curve, right? In other words, this is the compression portion of the compression curve, and that curve is staying rather smooth, right? You don't see a kink in the pressure curve like you do at this point here between image C and D, okay? And the reason for that is that you essentially have this period of time where the spark releases and you get this ionized plasma that's able to commence the chemistry of the fuel-air mixture, but it takes time for that chemistry to actually get going, right? Or at least to generate enough of these these radical species, right, and these various intermediate species. It takes time for those species to get formed during those chemical reactions, right? And this is literally how much time it takes, going from image A to image B to image C. And on the pressure curve, we're going from, say, somewhere around minus 45 to somewhere around 10 degrees, right? So nearly 35 crank angle degrees is how much time it takes for the chemistry to get itself far enough along where now you have a fairly high temperature pool of reactants, or a high temperature flame, really is the better way to say it, finally at point C, okay? Okay, so that's what's happening during your flame kernel development period, which again, I'll oftentimes refer to as the flame initiation period. Now, at some point, right, you build up enough radicals, the chemical reactions have moved far enough along during that chain reacting process, or that collection of chain reacting processes, where now the mixture is at a much higher temperature. And so all of this chemistry, all of this motion within the cylinder, it all generally accelerates, right? The combustion process has basically ignited, the combustion process has started, and you have a flame, and that flame is now ready to engulf the rest of the mixture and burn up and consume all of the available reactants. And that's essentially what's happening between image C and D. And we call that period of time the turbulent entrainment and burnup period, or you'll oftentimes hear me refer to it. In fact, I'll refer to it mostly through the rest of this lecture as the rapid burning period. And so the rapid burning period is basically, you can think of it as your main combustion event, right? This is where you would see something happen, right? You'd see a visible flame, you'd see a dramatic rise in pressure, right? And that's exactly what we see as we go from point C to point D to point E, right? This is our rapid burning period, and you can see how long it took for the flame to develop over the period of 35 crank angles. But then as we go from C to D to E, right, we're going from 10 degrees to 0 degrees to looks like about 18 degrees. So within a period of about 28 degrees, we nearly consume the entire fuel-air mixture, right? And so that turbulent entrainment and burnup period is a very rapid burning period, right? And that's exactly why I call it that, the rapid burning period, okay? And so, again, we'll come back to this and try to model these things in a little bit, but this is just meant to create some appreciation for you as to what's going on with spark ignition combustion. Now, eventually, of course, the combustion process is going to come to an end and things begin to die down, and that's, of course, the flame termination period, and again, you can see that in the Schlieren imaging with image F, where essentially, the analogy that I used in the face-to-face class was, this is sort of like a thunderstorm developing on the horizon, and image C and D and sum of F is when you have the most dramatic elements of the storm, and there's all kinds of thundering and lightning and heavy rain and hail, and it's just dumping massive amounts of energy on you. But then the storm basically blows out of the area, right? And then you have this calm clearness after the storm, and that's basically, to some extent, what image F is showing us. Okay, so let's take all of this that we've talked about so far and translate this into what we see in our pressure crank angle diagram, right? So we've already established how we have the spark release about 45 degrees before top dead center, which is the same as minus 45 degrees after top dead center. And so whenever you have your crank angle top dead center identified as 0, followed by numbers after that, we would refer to this as degrees after top dead center, right? So this would be degrees ATDC. And so this 20 here is, of course, 20 degrees after top dead center. And the minus 20 is, of course, the 20 degrees before top dead center, right? And so we have this point here where we have a spark release, right? Our cylinder pressure here is rising as a result of the piston moving from bottom dead center to top dead center during the compression process. And so our combustion initiation has commenced, right? We release the spark, and chemistry is happening. We're generating those radicals and intermediate species as we look at location A, B, and C, even though we can't really see anything in the pressure curve, which would suggest that we have any chemistry taking place. We then move from that flame initiation period into the rapid burning period. And now if you look real closely, you can see this little tiny kink here in the pressure data, right? You see how there's sort of a drastic change in the slope there. And of course, that's the result of the combustion process triggering from this flame, the flame kernel development period, the flame initiation period, to now the turbulent entrainment burnup, or the rapid burning period, okay? And so now we have fervent combustion that's taking place as we go from point D to point E, and eventually that fuel mass begins to burn, right? And so combustion begins to terminate here somewhere around point E as we go from point E to point F. And so the pressure was rising as we went from, say, 60 degrees before top dead center to, just before top dead center. The pressure was rising due to compression. But then we get to this point here where we have this kink, and now pressure is rising up until we get to top dead center as a result of both compression and combustion. But then when we get to top dead center, the piston reverses direction and continues to move down back toward bottom dead center, expanding the volume and having a tendency to decrease the pressure in the cylinder. But the pressure continues to rise as a result of the combustion process, right? So as pressure is now rising as we go from top dead center to this point F, right, which is near the peak pressure. Pressure is rising in this area here as a result of combustion. Well, combustion eventually begins to die off, and the piston is rapidly moving toward bottom dead center, expanding the volume, and those two factors combined causes the pressure to then begin to decrease inside the cylinder. And then once combustion ends at point F, then the pressure curve will more or less follow the kinematic expansion curve, which, as we talked about back in chapter 2, we can actually model that curve using the kinematics, okay? And so we're going to talk a lot about the shape of this pressure curve and how it's a function of things like spark timing and fuel air equivalence ratio and EGR level, for example. But before we move on from this slide, there's one additional item that I need to highlight, and that is this second curve that's on here, which is the mass fraction burn curve, okay? So the mass fraction burn curve is more or less just the result of the analysis of what we call the heat release of the fuel, okay? And so the heat release of the fuel is, essentially, and of course students in 611 will be learning about this in great detail, but the heat release is essentially the crank angle resolved release of energy by the fuel during the combustion process. And you may wonder, well, how is it that we determine that? We determine that by doing a first law analysis of our control system. In other words, we know how much energy we have in our cylinder based on the amount of mass that we've delivered to the combustion or to that fuel air mixture, right? We know how much fuel is in the fuel air mixture. And we're able to measure the cylinder pressure, right? This is the result of the cylinder pressure measurement that's shown on this figure. That, coupled with the ideal gas law and knowing what the volume in the cylinder, allows us to estimate the temperature of the gas. And by knowing the temperature of the gas and making some statements about the thermodynamic properties of the mixture, we can then determine the change in internal energy of the mixture. In addition to that, because we are measuring pressure and we know the volume of the cylinder, we can also calculate the work transfer out of the system. And then finally, if we make some assumptions and we do some analysis and do the best models that we can also estimate the heat loss from that cylinder and be able to build that into our first law analysis, which then gives us the heat release, okay? And so once we know the heat release, that is the amount of energy that is converted by the combustion process from the fuel, and we know how much fuel, the mass of fuel that's been delivered to the mixture, that then allows us to calculate the mass fraction burned, right? And so mass fraction burned is more or less telling us, right? So I'll often refer to this as MFB, and this is the fraction of fuel burned at any given moment. Okay, and so for example, at this point here, the mass fraction burned is 0.4, right? So that basically means that 40% of the fuel has burned at a crank angle of about, say, 5 degrees after top dead center, ATDC, okay? So that's what the mass fraction burn curve is telling you. And we're going to talk a lot about the mass fraction burn curve through the rest of today's lecture and into the next two lectures, okay? Okay, so we can spend actually quite a bit more time talking about this mass fraction burn curve and providing some specific definitions about how we characterize this mass fraction burn curve. Okay, so for this part, what I'm going to do is go to another set in my little notes here, right? And draw out for you what we mean by this mass fraction burned, okay? And so what I'll draw on the y-axis is x sub b, and x sub b is basically our mass fraction burn. So this is mass fraction burn. And I'll oftentimes use the acronym MFB to indicate mass fraction burned. And I can also draw on here where top dead center is. And so let's suppose that this is 0 degrees or TDC, okay? And I'm also going to draw, and so of course my x-axis then, that necessarily means that the x-axis is the engine crank angle. And then I'm also going to draw on here where 10% mass fraction burned occurs, and where 50% mass fraction burned occurs, and then where 90% mass fraction burned occurs, okay? Okay, and so, I don't really know. I mean, I'm just going to arbitrarily use numbers, and so I'm going to say that the spark releases at this crank angle here, and we identify that as theta sub s. And so theta sub s is the crank angle time when spark release occurs. Okay, and so it's basically more or less another way of saying spark timing. And so it might be, for example, 35 degrees before top dead center, could be 50 degrees before top dead center, right? That spark timing can vary, even right up to top dead center or in some perhaps odd and extreme cases, even after top dead center. But this is essentially when spark timing occurs, right? And so our mass fraction burn curve will initially look something like this, okay, where the mass of the fuel will burn and will rise in how much fuel actually burns, the mass of fuel that actually burns, in a rather slow fashion, okay? So once the mass fraction burned hits 10%, we then can define what we call theta 10, and theta 10 is that crank angle location where 10% mass fraction burned occurs. So this is the crank angle location when 10% mass fraction burned occurs. Okay? And we can also, at this point, define one of our first important parameters that we've already talked about, and that is the flame kernel development phase, or the flame initiation period, which we refer to as delta theta D, okay? And so that time between the release of the spark and 10% mass fraction burned is delta theta D, or the flame initiation period. So delta theta D is the flame initiation period. And it's that time or crank angle difference between 10% mass fraction burned and spark. And so we could say, for example, that delta theta D is equal to theta 10 minus theta S. Okay, so then once we reach 10% mass fraction burned, or essentially what the mass fraction burn curve will look like, is we'll then have, or we'll transition into the rapid burning period. And so at that point, our mass fraction burn curve begins to have a rather drastic rise in how the fuel is burned, right up until we get to about 90% mass fraction burned. And then it begins to taper off and ever so slowly rise to eventually what would be 100% mass fraction burned, okay? And so again, we can define this moment when 90% theta occurs, and it looks like it's close to TDC. That was just coincidental. But we can go ahead and define theta 90. And like theta 10, theta 90 is that crank angle location when 90% mass fraction burned occurs. Okay? And so likewise, just like we defined the flame initiation period, this flame development period, we can also define the rapid burning period, which we use delta theta B to identify the rapid burning period. And so that's the time between 10% mass fraction burned and 90% mass fraction burned. And so delta theta B is what we call the rapid burning period. And this is the time, or again, the crank angle difference between 90% mass fraction burned and 10% mass fraction burned. So we can define delta theta B as the theta 90 minus theta 10. Okay? Okay, and then, of course, the flame termination period is going to be from that point when we get to 90% mass fraction burned until we fully burn the fuel at 100% mass fraction burned. And for our purposes of what we're doing in Chapter 6, we're not so concerned with what happens during that 90 to 100% burn period. It has a large implication on various types of emissions, such as unburned hydrocarbons or unburned carbon monoxide, but we're not going to have time to get into those details this semester. So we're going to focus all of our time on the flame initiation period, this delta theta B, and the rapid burning period, this delta theta B. Okay? Okay, so now to try to make a connection between this mass fraction burn curve and the in-cylinder pressure, if I just real quickly go back to the Chapter 6 notes, you can see that that's already been done in this figure that's on the bottom of slide 3, right, this figure 9.14. And you can probably guess that they're showing this mass fraction burn curve on the same plot as the cylinder pressure curve to suggest that there's a relationship between the two. And yes, absolutely, there is a relationship between the two. And we'll talk about that relationship during the next lecture period. But before we do that, I first want to describe to you what the implication of the mass fraction burn curve and the pressure curve will have on what is our ultimate objective, which is to generate torque, right? You know, ultimately an engine has to generate torque. Yes, it has to do so efficiently, so we certainly care about efficiency. It has to do so with lean emissions, low emissions, right? So yes, of course, we have to care about emissions, but we first have to satisfy the first objective of an engine, or at least an engine designed to make power, and that is we have to generate torque, okay? So I'm going to take a step back. Before we continue a deeper discussion about mass fraction burn curve and its impact on pressure, we're going to take a step back and we're going to draw a sort of a macroscopic relationship between the torque of the engine and the spark timing of the engine. Okay, so let's go ahead and draw our torque. And we can even go back to our good friend brake torque, right? And so this will be tau sub b, right? So that's what we've talked about before, the brake torque. And now I'm going to plot this brake torque as a function of theta s. Okay, so be careful here. This x-axis is not crank angle degrees in the sense of how it is up here with the mass fraction burn curve, where I have 0 degrees, which is top dead center, right, indicating that the piston is moving through this range, right? In other words, the piston isn't, or in this plot that we have here, right, the piston is moving from through the compression stroke, right, reaches top dead center, reverses direction, and then moves down toward the expansion stroke, right? And so this is the engine crank angle for one given cycle. When I plot theta s, the spark timing on this axis here that we're showing our brake torque on, okay, this is now for a given cycle, right? The spark timing was a certain value, and I am generating brake torque as a result of that spark timing for, cycle after cycle after cycle. The engine is, say, operating in a steady state condition, right? And then I change my spark timing to a different spark timing, and now the engine is making a different amount of torque cycle after cycle after cycle on a steady state fashion. And so when I plot the brake torque versus spark timing curve, what I'm showing you is the torque value as the spark timing changes for a given steady state operation of the engine. Okay, so that can be somewhat confusing sometimes because, both of these figures are plotted as a function of some kind of theta, where, in this plot of mass fraction burn, that would be the cycle resolved crank angle, whereas in the figure of brake torque, this is the just indicating the crank angle timing when spark is released for a steady state operation of the engine. Okay, so this x-axis isn't crank angle resolved, as we would say, for a given cycle. Okay, so this brake torque as a function of spark timing basically looks something like this. Okay, and so we have, of course, if we have a certain spark timing that is very early, okay, and so in other words, if our spark timing is over in this regime here, right, over in this portion here, we have low torque. Our torque rises until we eventually get to a peak point, and then the torque begins to decrease as we go, as we continue to push the spark timing deeper or later and later into the cycle. Okay, so I'm using words like earlier and later, and those are actually not the words that we typically use. Okay, so the words that we typically use is if I change my spark timing, oops, that's the wrong item. So if I change my spark timing such that I move the spark timing in this direction, right, to the left of the, essentially that spark timing being released earlier and earlier in the cycle, then I would call that an advance in spark timing. Okay. Whereas if I move my spark timing later, so that the spark timing occurs later and later in the cycle, I would call that a retard in spark timing. Okay, so if you hear me use the words advance, that means that the event is occurring earlier and earlier in the cycle. And if you hear me use the words retard, that means that the event is happening later and later in the cycle. Okay, so now we have essentially this brake torque as a function of spark timing, and you notice that I haven't put top dead center on here. I don't actually know where top dead center would be. It really depends, right? And so, again, we could say that the spark timing for TDC at 0 degrees might result in this much torque. I don't know for sure. It just depends on the engine design. But let's just suppose for this conceptual description that this is where top dead center occurs for this given brake torque, okay, for this given engine. So again, if you take a look at this brake torque curve that we've drawn, you'll notice that there's a spark timing where we achieve maximum torque, okay? And so this maximum torque point has a special name to it, and it's what we call the MBT, or the maximum brake torque. Okay, so we have the maximum brake torque, and this is, of course, the maximum torque that the engine will achieve as we vary spark timing. Okay, so I can start off with a very advanced spark timing, and I'll get a relatively lower torque than if I begin to retard that spark timing, right? So I retard the spark timing, so the torque curve continues to rise and rise and rise and rise until eventually I hit a peak, and then my torque begins to decrease as I further retard my spark timing, right? And then the torque just continues to decrease and decrease and decrease as I further retard that spark timing, okay? Okay, now the spark timing that results in that maximum brake torque also has a special name, and it's the maximum brake torque timing, or theta sub MB, okay? So this is the timing, the spark timing, at which MBT occurs, maximum brake torque occurs. Okay? Okay, so there are several reasons, there's a few reasons, I should say, as to why the torque starts off low for very advanced timings, right? Why the torque starts off low for advanced timings, and then why that torque continues to increase as we go to higher and higher, or as we go to retarded spark timings, and then eventually it reaches a peak, and then it begins to decrease again as we go to later spark timings, okay? So let's first of all talk about why the torque has a tendency to increase from starting off at a very advanced spark timing and then eventually going to later spark timings where we reach the maximum brake torque. And so essentially the reason for why we have low torque for spark timings advanced of MBT timing is, first and foremost, we have something which we call an expansion loss, okay? And I'm going to put expansion in quotes here because this is oftentimes a point of confusion with a lot of folks, but I'll explain during our next lecture how we have an expansion loss on this side of MBT timing. The other reason why we have low torque when we're advanced of MBT timing is we have increased heat loss. And again, I'll talk about what that increased heat loss means in lecture number 40, okay? But you can already kind of think that if your spark timing is occurring very advanced of MBT, right? Say your spark timing is here, at this, say your spark timing is 60 degrees before top dead center, but your spark timing for maximum brake torque is maybe 30 degrees before top dead center. Well, what happens is you give that combustion process more time to initiate, ignite, and actually begin, and you start burning more of your fuel-air mixture all the while the piston is still moving up toward compression, right? And so you have increasing pressures due to compression, but then you also have increasing pressures and temperatures due to combustion. And so particularly those increased temperatures drive a higher heat transfer rate, right? Which at this point, of course, is going to be a heat loss. And the increased heat loss will cause you to have less energy available for transfer to mechanical work, which then, of course, necessarily means a lower torque, okay? Now, when you're retarded of maximum brake torque timing, you really just have one major issue that's causing your decrease in torque, and that is what we call expansion loss, okay? And these two expansion losses, both on the compression side as well as on the expansion side, is essentially what we would say a combustion phasing issue, right? Combustion is either phased too early, meaning that you're releasing too much of the energy before the piston reaches top dead center to make full use of that expansion stroke, or you are phasing the combustion too late, such that you're not making full use of that expansion stroke, okay? All right, well, we've run out of time for today, and this is, in fact, just as far as we got when we did the face-to-face lecture, so we'll go ahead and complete for today here, and we'll pick this up on lecture number 40, where we'll pick up this brake torque versus spark timing curve and begin to relate this to our mass fraction burn curves, and then create a nice little model for us to be able to analyze those two phases of the mass fraction burn curve, the flame initiation period and the rapid burning period, and then relate those two parameters to how changes in spark timing, fuel air equivalence ratio, and EGR level affect our mass fraction burn curve, our cylinder pressure, and then ultimately our brake torque curve. And then that'll complete the semester. So thank you so much for your time and attention. If you have any questions, send me an email, and I look forward to lecture number 40. Take care. Bye-bye.